Good morning. This is going to be an update on Project Leyden. You might have heard a little bit about it. This is all about capturing lightning in a bottle, as we like to say. Valhalla gets its codes like a class, works like an int. Leyden is capturing lightning in a bottle. So the goal of Leyden is fairly simply stated. We aim to improve the startup time, warm-up time, and footprint of Java programs. That's simply stated, but it's rather ambitious after all. This platform is 28 years old, and these startup time and warm-up time and footprint have been a problem since pretty much the very beginning. But here we are. This is, of course, especially important in the cloud, where competing platforms like Go are, quite frankly, eating Java's lunch in this regard. How do we propose to achieve this end? Well, we've got a few tricks in mind. One is we aim to shift computation temporally, forward and backward in time, later and earlier, later in the hopes that it won't always be necessary, earlier in time from runtime to build time, or some earlier phase even in between. We also want to constrain Java's natural dynamism to enable more and better shifting. The thing about shifting is it often requires some level of static analysis, and static analysis in general of a dynamic language of Java, like Java is hard. So we'll look at introducing a spectrum of constraints on computation and dynamism. We'll do these things selectively per the needs of each particular program so that developers can choose which constraints to accept and which computations to shift. It should be up to you. And finally, we will do these things compatibly. We will evolve the Java platform specification as needed to permit all the shifting and constraining so that you can be assured that your program will have the same meaning after it's been transformed. So let's try to unpack all this a little bit. Shifting computation. Well, if you think about the computation that goes on in a JVM process, there are sort of two kinds. There's computation that's expressed directly by a program, for example, invoking a method. And there's a bunch of computation work done on behalf of a program, for example, compiling a method to native code. That's never something that you actually ask for. It just magically happens, and usually the JVM does a great job of doing that just in time, as they say. So Java implementations already, of course, have features that can shift computation. Sometimes they shift computation automatically. For example, compile time constant folding, it just happens. Garbage collection just happens. Garbage collection is an example of shifting computation later. Constant folding, of course, is shifting computation earlier. Other forms of shifting computation that we already have are optional. They're things you have to ask for. Ahead of time compilation shifts things earlier. You have to configure your system to do that. Pre-digested class data archive, CDS. You have to use the right XX flags to make all that happen. Lazy class loading and initialization. That's something that you can express in your code today using things like the well-known lazy class holder initialization idiom. So there's already a fair amount of shifting going on in Java, and all of it is compatible. All of it preserves the meaning of your program per the specification. So in Leyden, we will explore some new ways to shift computation. Some kinds of shifting will likely require no specification changes. For example, expanding lambdas into ordinary bytecode. Lambdas are implemented with Indy, of course, today, and they expand at runtime into actual code. So an obvious thing to think about shifting is, oh, well, let's do that expansion at build time, shifting that computation earlier. Other kinds of shifting probably will require specification changes. For example, eliminating dead code, especially vast quantities of dead code. Sometimes this is called stripping. This is effectively shifting computation earlier. Why does this require specification changes? It might not be obvious, but if you remove a bunch of code, there's always the chance that some other code expected to be able to reflect upon it. And having that disconnect if the code isn't there, to cover for that, we're going to need some sort of change to the specification, probably maybe even some API such that you can request that something not be stripped or that its metadata be saved somehow. Finally, we'll look at other ways to shift computation that we'll express as new platform features that allow you to express temporal shifting directly in your source code. For example, the lazy static finals that John has talked about sometimes. So what about constraining dynamism? Why would we want to do that? So shifting computation, as I mentioned, often requires doing code analysis, but Java's dynamic features make code analysis really difficult. One approach to coping with that, of course, is to impose a closed world constraint. Closed world constraint says you're a closed world, you can't do any more class loading, you have to accept severe limits upon reflection, and given that constraint, you can do some impressive things. The problem is that many applications don't work under this constraint because dynamic class loading and reflection are fundamental to so much existing Java code. And also, many developers aren't willing to live with this constraint because the tools that use it often require to maintain a bunch of fragile configuration files and endure unusually long build times. So in Leyden, we will therefore explore a spectrum of constraints, up to and including the closed world constraint probably, such that you can selectively degrade Java's natural dynamism to enable more and better shifting of computation. You get to choose how to trade functionality for performance. So how are we going to do all this shifting and constraining? Well, we'll do it with a new kind of tool called a condenser. And this is really sort of the key new concept of Leyden is this condenser idea. A condenser is a tool in the JDK that performs some of the computation encoded in a program image ahead of runtime, thereby shifting it earlier in time. It transforms the image to a new, faster image that can contain a bunch of interesting things. For example, it can have new code, ahead of time compiled methods. It can have new data, serialized heap objects. It can have new metadata, some preloaded classes or preloaded class metadata. It can also encode new constraints upon later condensation phases and ultimately on runtime. For example, it can say that, oh, this set of classes can never be redefined. That could enable some interesting shifting and optimization. Condensers have three critical properties. One is that they are meaning preserving. The resulting image, you give an image to a condenser, it does a transformation on it. The resulting image has the same meaning as the original. It is compatible. Condensers are also composable, so the image output by one condenser can be the input to another, and a particular condenser can be applied multiple times if needed. In fact, if you think about condensers, there's an analogy here with optimization passes in a sophisticated compiler, right? We stand the risk of running into the same sort of problem where you've got a bunch of condensers and you need to choose what order to run them in, whether there should be a loop in your condenser pipeline, whether you should reapply condensers at certain times, but that could be a good problem to have. Finally, condensers are selectable. You choose how to condense and when. If you're just testing or debugging your code, then don't bother, just run normally, right? The meaning is going to be the same. Insofar as shifting computation requires you to accept constraints, you can trade functionality for performance via the condensers that you choose. Now, an important consequence of the condenser model is that performance is an emergent property. The performance of your program depends upon the condensers that you choose. So in theory, given sufficiently powerful condensers, if you shift enough computation earlier or later in time, or both, you might even be able to produce a fully static native image. But of course, this will likely require accepting many constraints. Because of this, Leyden doesn't need to specify fully static native images directly. Instead, it just needs to enable sufficient shifting of computation and constraining of dynamism so that fully static native images can just fall out as an emergent property. So last October, we published a roadmap basically, areas in which we see we need to do work. One, of course, is introduce the concept of condensers into the Java platform. We need to evolve the Java platform specification to allow meaning-preserving whole program transformations. This is not something that we have today. We also need to evolve the runtime image format to accommodate new code, data, and metadata, or maybe we even need a new runtime image format. We just don't know yet. Second, we need to explore new ways to shift computation and constrain dynamism. This is really, I think, going to be the meat of the project. And finally, there are various related improvements that are worth looking at under the slightly more general umbrella of making Java more fit for the cloud. So I'm happy to say that here in July of 2023, we've made some good progress. In terms of introducing condensers, Brian, Paul, and I recently published a note on Toward Condensers, which basically introduces a simple, immutable, data-driven model of application so that condensers can be expressed in terms of the API for this model. And a condenser is basically a transformer of instances of the model. And Paul has prototyped a couple of simple condensers against a prototype of this model, and you will shortly be able to find the code in the Leyden repo in a prototype branch. In terms of shifting computation and constraining dynamism, there's been some good early work from Dan Heidinga, and he's recently pushed that into another prototype branch in the Lambda repo for pre-generating Lambda classes. Brian published a note on condensing in indie bootstraps. There's a question here about, well, if you want to expand something like a Lambda bootstrap, how should you do it? You could write a new condenser for every kind of bootstrap, which seems like it's going to be a maintenance problem, or you could somehow figure out how to evaluate the existing bootstraps and condensers, which seems like a hard problem. Brian actually suggests that, well, neither of those is the right answer. The right answer is to adjust the bootstrap programming model instead, so that you can express bootstraps that are operable in either phase. Also, under shifting computation and constraining dynamism, Per Minborg and Maurizio Ciamatamorte recently published a draft JEP for computed constants. This is an API-level approach to some of the same problems that lazy static finals aim to solve. The interesting thing is that computed constants could also be the basis of shifting computation earlier in time with an appropriate condenser. And finally, John and crew have done some really cool experiments in shifting speculative computation, which you will hear about in just a moment. And there's also been some good work in related improvements. Jiang Li has been working on hermetic application packaging, and Severin has prototyped a J-modulus form of J-linking. So this is good progress. There's going to be more. If you'd like to find out more, the URL for the project page is up there. Please come and join us. And here's John.
Thanks, Mark. Good stuff. I want to pick up on Mark's discussion of the static dynamic interchange. This is an image that I had an artist draw in 2010. I've been worried about Java's static dynamic interchange for a long time. Worried, bemused, fascinated, challenged. Probably many of you also. Java is not only a static language, although it has many static aspects. It has also dynamic aspects, but it's not only a dynamic language either. And so there's a dilemma between static and dynamic. Static gets you one set of things. Leyden very much cares about static analysis. But Java very much cares about, in the end, being dynamic. So do you choose one and lose one, or can you have both? And the answer of Java to date has been, you get both. You get both, we'll figure it out for you. And that's what makes being a JVM engineer so interesting, because you've got to have this thing that looks static enough to optimize, as well as C code can be optimized, for example. And on the other hand, it looks to the user fully dynamic. The secret to this is speculation. HotSpot speculatively optimizes literally hundreds of conditions and states, and has tactics that have grown up over the last quarter century from centuries of engineer years to manage the speculations in such a way that when they succeed, you get performance. And when they fail, you get less performance but correct execution. And then it warms up again, finds a new hotspot, that's the name of the virtual machine after all, finds a new hotspot, makes new speculations, and soldiers on. And then if you change it again, it responds again. That's the way the HotSpot virtual machine works. In Leyden, we're taking on the challenge of doing the work to optimize based on speculations and other conditions and shifting it. What more natural thing to do than to shift, say, 60, 120 seconds of JIT work from the middle of your application to somewhere else where it doesn't get in your way. So that's the challenge we took up. We've been looking at this on paper for a very long time. But since the Leyden roadmap was rolled out, the hallway conversations increased. And last March, some of us started cutting code, and that's what I'm here to talk to you about. This is really new stuff, but I'm super excited by it. In the end, it's as Mark says, you can give users tools to shift computations, including JIT computations and startup computations, so that the user can use these tools to drive startup and warm up, which I will define in a moment, into the noise, and without giving up any compatibility. Leyden does contemplate, as Mark said, constraints, the user accepting constraints in exchange for further performance. But the work that we've been doing on the VM recently doesn't add any new constraints. So that was a surprise to us. We expected to have to add constraints, but it seemed there was a workaround, a speculative optimization that could replace a hardwired optimization based on constraints. So that's nice. No new code changes, no new constraints. Let's see how this works. First, I have to tell you some definitions. This is, I'll skip over this slide quickly, but basically startup activity is what it takes to get through your first task. Warm-up activity is what it takes to get to peak performance. Warm-up may take 10 tasks. It may take 1,000 tasks. It depends on your application. It depends on how broad and flat and warm your application is. If it's a micro benchmark, you're going to get to peak fast. You're going to warm up to peak fast. If it's a big application framework with lots of submodules, as most of us know in this room, it can take a day to warm up. So the time scales vary to an insane amount. There's no one time scale where warm up happens. I will say that the analysis or the user model that I'm going to explain to you here does assume that there is something like a task that your application can do repeatedly. Not all applications are like that, obviously, but most are. But you could also say, even if you don't have a task structure, you could say startup is not after the first task, since you don't have tasks, but it might be after you get to 80% rather than 95% of your eventual peak. Funny thing about all these numbers is it depends on a number that you don't get to until the very end, but then you retrospectively model everything, all of your metrics relative to that peak number. The peak is like, when you really dial into the best performance that the system's going to give you. Here's a graph that shows what I just said. Initial activity, startup happens, and it takes some time. This is a graph where lower is better. The time is the height of the graph. The gray thing is what you could have if you could get all your wishes. The gray thing says, I'm going to start up doing just the minimum amount of imperative work in my CL inits. I'm not going to assume a complete program transformation. I'm just going to assume my CL inits somehow run really fast. And then everything is just optimized at peak already just because magic happened. That's an ideal, okay? Everybody agrees that's an ideal. That's the gray line there. The blue line is what happens typically. This is a model, but it's a model founded on numbers that we routinely see. I'm going to show you a model first, and then I'll show you the real numbers, which are noisier, but you can still discern their relationship to this model. So the area under the curve is what we want to fix, in particular the area between the gray and the blue. And you'll notice that the area, the tall triangle at the very left is smaller in area than the large swath of warm-up effort that goes all the way to the right. This is again something we discovered as we got our fingers dirty in doing some prototyping. We had a million good ideas for making startup fast. We started with such ideas, but they don't matter. They buy you a few milliseconds at the beginning of execution, and then your wins are gone at that point. The real high leverage move is to work on warm up, and that's what we want to do. We want to be able to drive the blue curve down. Here is a larger scale where suppose you have 100, whatever it is that you're doing in a row. The warm-up can take 100 tasks, but our challenge is to take that whole warm-up curve and get to peak faster, which means reducing the area in that stippled point. Notice on this time scale of 100 repetitions, startup doesn't even register. It's a blip. In order to work this, our current technology is called tiered compilation in HotSpot. How many of you have heard of tiered compilation? Okay, this is a smart room. All right, there are 5 tiers starting from 0. Tier 0 is the interpreter. Tier 1 is C1 code that has no profiling at all. It's only rarely used. Ask Igor. I forget when it's used. Igor is the world expert, I think, on compiler JIT policy. He worked on this stuff with me. Thank you, Igor. Tier 2 is entry point profiling, only invocation counters. Tier 3 is full profiling, the same profiling the interpreter does, types and branches. And then Tier 1, 2, and 3, all of those things spin up quickly because C1 is a fast compiler. But Tier 4 is the slow one. It's C2, or if you've got Graal plugged in, it's the Graal compiler. It's slow. It takes maybe an order of magnitude or more time to compile the same amount of code, but it does a great job. It uses data produced by the earlier tiers, so it's important not to skip forward immediately to Tier 4. You have to invest some time gathering profiles before Tier 4 really pays off. Tier 4 can also speculate. If it fails speculation, then that's called de-optimization. What I was explaining to you earlier about how speculative optimizations work. As long as you speculate correctly, you win. When you lose, you still win because you just go back and re-optimize. If you win big. If you lose, you still win. Here's a graphical description of what I call code states in the compiler in HotSpot. These are not user visible states. They're transparent to the user, but they're real. They affect performance. I think I don't have to explain that. I just explained it verbally on the previous slide, but that shows in a nutshell how it works. Notice the cycle of de-optimization back to the interpreter, so that you can cycle through the Tier 4 many times. So the speed-ups you get don't affect program correctness. They don't impose any constraints that they aren't willing to speculate away from. But they do give you good performance. And startup is handled by the VM, which resolves symbols, runs class inits, the famous CL init. It runs invoke dynamic bootstrap methods to materialize lambdas and string concat methods and who knows what else. As the application proceeds over time, then warm-up takes over, and that's when when the hotspot is gathering profiles and eventually running the JIT. And this, like I said, it can take minutes of JIT time to get you to peak, depending on your application. If it has a lot of code, it'll take minutes of JIT time to get you to your peak. And you got to put that time somewhere. So wouldn't we like to shift that as part of Leyden? Well, keep paying attention. So the mechanism that we have worked with to make this work is pretty simple. It's called a training run. You run a training run, which is like something that exercises the paths that you care about in your program. You run it in a special mode which says, please watch me. I'm going to do something that I need optimization for. So the training run gathers information, and then that information is later used in a deployment run. That's the big idea for now. It seems to work well. I'll show you in detail. So some of the states that come out of initialization, such as a loaded class in metadata, can be recorded in a training run for deployment. And what I just said is old news. Yoy Lam has been working on CDS for many years. It's brilliant work. CDS, Class Data Sharing Archives, do exactly this. You start the application up just enough so it can smell its class path and do some basic stuff. And then it checkpoints the loaded metadata back down onto disk so it loads faster the next time. That's exactly a training run followed by a deployment run. So what we're doing is, in a sense, very old, but there's some new parts to it. One of the new parts is persistent profiles. That's an Igor idea. The idea there is, since CDS is good at saving metadata and profiles are metadata, maybe we could save the profiles as well as save the class metadata. It means running the application a little longer in training run through some of its paths to collect profile data. So we did that experiment in April. It was very interesting. It got some initial wins. It was helpful. And then, of course, if you're going to save profiles, that's good, but why not save JIT code as well? That would be really cool. So that was something we did probably starting in May, and that's really helpful. But the theme is a training run plus a CDS to catch your information gives you a deployment run that starts up with the benefit of the stuff in the CDS archive. How many of you have used CDS? Okay, good. You're familiar with it. So this is one more level of detail how this works. I want to point out that the training run should start up your application at a minimum, right? Otherwise, it's not gathering any information. It should also, in fact, ideally warm up your application so that you gather profiles and code for your application. During this time, all that stuff is collected into CDS archive and or logs. Optionally, if you collect into logs, you can use a tool to combine multiple logs and then funnel the log information back into the CDS archive. The final step that creates the CDS archive and makes the application ready to start up with all that benefit in place is called distillation. That's a condensation variation. It's like a terminal operation on a stream. And so when you execute it, you're running a deployment run. It starts with all the benefits that come from whatever was stored in the CDS archive. This is some of what I'm telling you is on paper only. We have not actually done the workflows that serialize and deserialize the information into logs. That's very basic. All of our prototyping so far has been focused on a linear workflow where you take a CDS archive, you run it for a while, and get better CDS contents out of it. So that's what I call a linear workflow. But a branchy workflow where you have multiple inputs and outputs is easily done as soon as you invest in the serialization into log files and then reading them back in after tooling. And then one thing that we have obviously want to build on top of this, but we haven't even started, is auto training mode, which is where you don't even have to say this is a training run. You just start running your application and the system says, that looks like that could be a really good training run. I think I'll pay extra attention. And then the second time the same thing runs, you benefit from an invisibly, transparently saved CDS archive that had the information from the designated training run that was designated by the system implicitly. That's a lot of stuff, but I want to say as a sort of a bottom line, this kind of framework and tooling seems reasonable for you to use as long as you're comfortable making a benchmark for your application. Seems like a reasonable contract. Make a benchmark, run it in training mode, get the CDS archive. Now you got something that probably runs better. Why are training runs effective? Well, it's back to the static dynamic thing. Dynamism is not really fully used all the time. Dynamism is an option, but in the actual path that's taken through all the options of dynamism by a given run is pretty stereotyped. So the same kind of types show up at the same places, the same branches get run often, other branches don't get run at all. That's what you capture in a profile, and then you speculate on it, and it has the effect of sort of turning what was dynamic and unoptimizable into something that feels static. Basically, a training run is using a Turing machine to predict the future activities of another Turing machine, whereas a static analysis is using, say, a finite state machine to predict the future activities of a Turing machine. So there's pros and cons, right? It's a finite state machine, theoretically easier to manage. It doesn't loop forever on you. Turing machine can more accurately emulate the ultimate Turing machine, but can you prove it's going to accurately emulate it? Well, no, there's a theorem about that. So what are you going to do? Java, like I said, it's not about choose one, lose one. It's about choose both. We're using all of the above techniques. But I will notice that if you have only a static technique, it tends to be what I would call needy of constraints. It says, well, I see you're giving me this input, and I really want you never to change it again, please. And so that's kind of what it feels like sometimes as a user of these things. You say, okay, well, I guess I'll let you. I guess I'll sign on the dotted line for that contract. But it's easier if you don't sign those contracts, and the speculator takes care of optimizing through your past behavior under the assumption that it's going to be your future behavior. So obviously, if you use HotSpot, whatever it does to puts in the CDS archive, you expect it's going to execute correctly if you hand it surprises during deployment, right? If you load a new class and it does completely new stuff. How many of you have apps that sometimes do completely new stuff, right? Yeah, that's what an application framework really is, right? Or a library with like multiple entry points or something. So this approach copes well with all those things that we're used to in Java. And of course, during deployment, we have some policies to continually re-optimize. If something changed and the originally emitted code is no good, you just re-optimize, that's all. It does cost time at that point, but presumably it's because you needed to do something new that needs a new optimization. So like I say, we've been working on this since March, but I mean, as of like days ago, this stuff is ready to share. We didn't know it would work, but it does. So we can persist many kinds of states, and speculating is actually helpful. And the tier 4 still works. I mean, the C2 JIT, or I assume this works with Graal too. We had to make some adjustments to C2, so I don't know about Graal yet. But it works, and it uses the existing JIT in a speculative mode that's slightly different from its usual speculative mode. But the policy challenge, of course, is to combine these things smoothly. States we capture, I've already mentioned, but I will point out that we can capture indie states. That was a surprise to us. The CDS archive can just have a pointer to the method handle and the hidden class, and there's no need to like give it a static name or turn it into bytecodes early. It's just an object in the CDS archive. So that turns out to be a big win if you have lambdas in your code. And once these things are captured, they look static under speculation. It can be made safe and sane. We have some theoretical ideas about this, but the basic key idea is that there's this thing that happens before main called pre-main. And pre-main is where imperative actions happen that are the shifted computations that come out of main and go before main. So you could write code in pre-main, but in fact, the code in pre-main is usually written for you. And in all of our prototyping, it's written for you by just inspecting the training run. So that's where initializations might take effect. That's where JIT stuff happens. And then, of course, some pre-main states are so well defined that you just dump them in the CDS archive and they're there when it starts up. It's as if pre-main ran instantly. But other pre-main events might be interesting to, in the future, consider as like user codable startups that then the system tries to optimize in a way that happens faster. So archive code states come out of this training, and nominally their compilation is put into pre-main, but in fact it's pushed all the way back into CDS. We did both, by the way. We experimented with both. So code that's not exactly hot gets put into tier 2 and it stays there. There's no reason to put it into tier 4. But code that is hot on the training run is kept. It's kept with we thought it would not load so fast. We should have listened to Azul or somebody like that did some of these experiments earlier. But in any case, code loaded from the archive loads up to 500 times faster than compilation. So that's pretty cool. We thought C1 was fast, but man, loading is really fast. And of course, loading from the archive is just another exercise of the same HotSpot infrastructure. If you know HotSpot, you know that the JIT puts code into a byte buffer called a code buffer, along with some relocations, and then when it installs it in the code cache, it just copies those bytes over and then runs the relocations. It's like relocating a .o file. Well, guess what? That same mechanism works just great for this too. You just put the byte buffer into the CDS archive and the relocation information, then zip, and it goes into the code cache when you need it. So the savings come from two kinds of avoidance. One is from JIT avoidance, right? That's 60 seconds or 120 seconds of work to get to peak. And the other is from interpreter avoidance. You don't need the interpreter to gather profiles, so you just install the code at the earliest possible moment. Here's the updated code state diagram. There's 3 new bubbles. There's the C1 that I talked to you about, the warm stuff. The 2 tier 4 bubbles, one is for before inits have run and the other is after inits have run. This is a very marginal improvement, but we kept it because it was a cool idea. And it does give you small improvements on some benchmarks for startup, not warm-up. The basic idea is let's have C2, the optimizing compiler, do a mode where it puts in initialization barriers so it pops back to the interpreter if it sees an uninitialized class, but it doesn't discard the code. It just, next time you execute it, the class has been initialized and it takes the branch it wanted to take. But that's no good because those tests cost time, so we replace it as soon as all the classes are loaded by a push into the code cache of the write code. That's the thing on the far upper right. So then this gets us ideally to a picture more like this, where the green curve is what you've got. You get close to peak almost immediately. During startup, you preload and prelink classes, which is just CDS du jour. We've always had that. We pre-resolve indie-condy sites. That's new. We add partially optimized code that I just explained with the init barriers. That is present just at the very beginning of time, and then it quickly swaps out. And then the green line at the bottom, you can't even see the green line at the left, but it's there. The green line at the bottom is your CDS code that's ready to run. And here's a cumulative version of it that shows it's just the integral of the previous graph. During the long-term life of the application, there might be reprofiling and reoptimization, as I said earlier. So here's a case study. We made a Java-C benchmark. Java-C is a sort of a flat, warm program. It has a lot of code in it. It takes a little while to warm up. In fact, Java-C seems to us to take hundreds to thousands of repetitions, maybe even hundreds of thousands, to warm up fully. This means that it's a good candidate for this technique. So the first task is your first file you compile runs through all the startups, so you want that to be fast. But then you go over and over again compiling the same kinds of files. They're small files, 100 in a group. We found that we could put a lot of useful artifacts into CDS to support this particular use case. And this made us realize, gee, we should have been more friends with Yoy because he had some really good ideas. Thank you, Yoy, the CDS author. So he joined our team and actually gave us tutorials how it works. It was great. It was great. So it's been underutilized, but we're going to fix that. When the classes are loaded and initialized, then we say the dependencies for the good code ripen. And when all the dependencies for a good code ripen, then there's this push notification that pushes the code into the code cache, and that's when you're getting into towards peak. This is work in progress, but I think it needs lots of tuning. We're going to need help on this, but the pieces hang together surprisingly well. So here's the actual numbers, not fake numbers. So what really happens. That's not bad. And this is, like I said, early days, stuff we've been working on since March. So let's take that and let's make it better too. Here's at a longer scale, out to 100 runs, it starts to get noisier because there's like GC artifacts and who knows what. I mean, HotSpot's really hard to, it's a busy place. It's hard to keep track of everything going on. Here's the cumulative diagram. The green one is the new one. The blue one is the old one, and the gray one is the one that we wish we had if we could like get instant optimized code in our dreams. And here's the very longest. This is 1,000 runs. There's noise here partly because we're down into the milliseconds and the quantization noise is to the 1 millisecond level. I think that if you look super close at this, the baseline is still slightly better than the green line, but it's early days. So it works. There are lots of things, there are lots of improvements that we can do, and cumulatively they push the blue line down to the green line. There's no one technique that's the magic bullet, so let's find some more too. Let's keep mining out these hidden potentialities of the HotSpot framework. There are multiple timescales that are important, and so we also want to use JIT optimization as a fallback. Tuning is important. The numbers we're showing you here are not very well tuned. So every JIT engineer knows that tuning is a way of life. Second case study, Spec JVM 2008. Here I'm not showing you the ideal, just the blue baseline again, the green pre-main again, and just for grins, a red line showing what happens when you just use CDS, app CDS in particular. So the red line improves things, I guess, a little bit, but you'll notice the red and the blue line both take a long time on startup, whereas with pre-main and JIT caching, the green line starts basically within the noise at peak. So that's good. This one is kind of artificially good because the task structure is do a bunch of stuff for a second, do a bunch of stuff for a second. So basically the first 100 milliseconds is probably the real startup artifact, and it's just hidden in the first second. So that's why the green line is so low there. Like I promised, the startup is lost in the noise. Sometimes that's the only interesting win. Sometimes your warm-up is good enough and your startup is what you want to improve sometimes. Sometimes it's the other way around. Yeah, more policy work is needed. Third and final use case is Spring Boot. So here, it's not a micro benchmark of any sort. It's a application framework. And so we took an accepted benchmark that measures startup of your application framework. It's Hello World, I think. That's what it is for Spring Boot. I'm not very familiar with Spring Boot. We collected two sets of numbers. One was wall clock time of the VM execution, and the other was the self-reported time from the Spring Boot framework. It said, here's how long I took to get to Hello World. And his number is suspiciously short, so it didn't capture all of the very early initialization effects. So I prefer the numbers on the left, even though they're larger, because they have more information in them. But I gave you both just to show that we collected both numbers. This is an average of 3 runs. There's a lot of options here. Let me walk you through it real quick. The blue one is the default. The red one, as in the previous one, is the app CDS only. And that's a good win, right? App CDS is cool stuff. Again, thank you, Yoy. Then we get into pre-main stuff. So the next 3 bars are the pre-main with code, with JIT activity time shifted into the training run. And there's 3 flavors of that. There's one where there's no indie snapshotting, so the indies have to be run in the deployment run. The second one does do indie, but doesn't do the CL init hack, where you have init barriers and specialized tier 4 code. And then the last one adds the specialized tier 4 code. You can see that from going from yellow to green to brown, the yellow one is going from yellow to green is adding the indie snapshotting. So the lambdas are all pre-cooked in the CDS archive. That gives you a good bump. There's a very modest bump from having special code that handles initialization early days and goes to the interpreter to manage initialization. But it's still worth something. So like I said, we put it in. The last 3 bars are the same analysis, but with adding in a special hack for Spring Boot called AOT. I don't understand what it is, but it has something to do with making the classes more visible to CDS for archiving, right? If you know what it is, then you can explain it to me later. But the Spring Boot AOT mode is beneficial, obviously, but we make it even more beneficial. So the interesting thing here is that the two optimization techniques at two different layers, Spring Boot AOT and pre-main, they synergize. They don't interfere. They combine in a synergistic way. So that's the sign of a well-designed optimization when it doesn't screw up other optimizations. So everything works well together. Love that app CDS. Love the time shifting of class loading and also code archiving and Indy. So cool stuff. Where are we at now? We're at the end of the time as well. So pre-main activities are currently derived automatically from training runs, as I explained. So the optimizable states that we get from pre-main are dumped into the CDS archive. In the future, user-defined activities might be dumped as well, specified as well. That will lead us into this world of pure intrinsics, where a user can say, yes, I will trust this Lambda metafactory thingy-like thing as a pure intrinsic, so please execute it ahead of time and capture the results. If it's system get time of day, that's not pure. Looking at the clock is not pure. But if you do something that might as well be done in the training run, then we want to be able to mark code that is good to run in the training run and have that be run then if possible. This is a spec change, so I'm not saying we did anything in this space yet, but I think it's in our future, being able to mark functions as pure intrinsics to be time shifted, even though you can't tell from analysis whether they look at the clock or not, or whether they flip a coin. If they flip a coin, then you might want to reflip it during deployment, or it might be good to flip it at training. We don't know. The programmer has to choose, right? In any case, none of this that we've done so far trades away any of Java's natural dynamism. There are no new constraints on the programming model. It's CDS on steroids. We need more workflows. Currently, our prototype is flag soup. Sorry about that if you play with it. We got to make the user model better. But we're working on it. There's lots to do. Please join us.